one that's going to have a somewhat less clear pattern to it. So let me show you how you might look for it. Again, if you're looking for a pattern to write it back into the series part, into the summation part, then your best bet is not to multiply out or divide out or reduce any of the constants. Just don't do that, because that will make it harder to see the pattern. It's kind of a weird situation. So let's take a look. We're supposed to find a Taylor polynomial of degree 2 centered at a equals 1 that approximates the natural log of the quantity 2 times x. So in order to do this, the first thing we need to do is find our nth derivative. And then on the other side, next to that, we will compute the nth derivative with the center plugged in. And in our case, the center is 1. Ooh, the lag is terrible. Okay, so let me shut down a window or two and see if that helps. Okay, hopefully that will help. Okay, so do I have anything else I can close down? I think the rest of it's going to have to stay open, at least for now. Or I could pull up something else, but okay. So if we're looking at this, the first thing we want to do is go through and compute all of the derivatives. I find it's usually better to do it sort of one step at a time and not try to rush it too much. So let's do the nth derivatives first. There we go. Okay, so the zeroth derivative is the function itself, and that is just going to be the natural log of 2x, right? So the zeroth derivative means don't do the derivative, basically. And then the first derivative would be the next one. And derivative of natural log is going to produce a rational function, 1 over u times the derivative of u. And again, I'm going to leave it as 2 over 2x. Yes, it would reduce to 1 over x, but if I do that, I may lose the pattern that's developing. So I'm just going to leave it the way it is right now. Now, this only asks for the second degree. We'll actually go a few beyond that because the second degree is probably not enough to find a pattern. So we'll do the second degree, but we'll also look for the Taylor series, which is more what Dawn is asking about. How do you come up with the formula again? So we'll stop after 2 and get the Taylor polynomial, and then we'll continue and do the Taylor series. So the second degree would stop after the second derivative. And to do the derivative again, you would want to think about this one here, the 2 divided by 2x, as 2 over 2 times x to the minus 1, which would give me a negative 2 over 2x squared if I did the derivative again. So if I'm looking for the second degree Taylor polynomial, the next thing I need to do is to plug in the center for those values. So the center is 1. So f of 1 would be the natural log of 2, which, I mean, there's not much I can do with that. It's irrational, okay? And then for the second term, I'm looking at the first derivative at 1, which would give me 2 over 2, which would reduce to 1, but for now we'll leave it as 2 over 2. And the second derivative, oops, not at x, instead at 1. I'm having trouble getting it to go. Whew, boy, it's slow. Okay. We'll see how long this lasts. I probably should have shut down my computer and restarted it. Okay. Coming back. 1. The second derivative would give me -2 over 2, which would give me a -1. Okay, so writing out the Taylor polynomial of degree 2, remember your formula. For the second Taylor polynomial, it's going to go from n equals 0 to 2, the nth derivative at a over n factorial times x minus a to the nth. Okay, so this is the formula that we need to use. And in order to apply the formula, we're just going to allow n to be 0, then 1, then 2. So my first constant is up here, the natural log of 2. And the natural log of 2 divided by 0 factorial is still natural log of 2. And this would be x minus 1 to the 0th, which is 1. So the first term is just natural log of 2. So we could call this P2 for the second polynomial. You could call it T2 as well. P2 works for both Maclaurin and Taylor, so I kind of prefer that. So this would be the natural log of 2. All right. And then for the next term, we would take the 1 that is here, the first derivative at the center, divide by 1 factorial. It's like my n got lost. And that would still give us 1 times x minus 1 to the first. So we would just have a 1 times x minus 1 to the first power. That would be the next term. And then the last term for the second degree, or the second derivative, would take -1 and divide by 2 factorial to match the order of the derivative. So this would give me plus a -1 over 2 factorial x minus 1 quantity squared. So that is P2. That's all this question asked for. All right. However, if we want to keep going, what I would do in order to find the actual series is keep going with this pattern until I could see something starting to develop. And I really don't see it yet. So let's keep going and find the third derivative. And then maybe we may need to go past that. So let's find f triple prime of x, which, let's see, what would we end up with here? We could think of this as -2 over 2x to the -2. And that's going to bring another -2 to the front. So I'm going to have a -2 over 2. And then it will be x to the -3, which will drop that down to the denominator. Did I do that correctly? Looks like it did. Okay. And then if I did the derivative again for the fourth derivative, what would happen? Well, then the 3 would come to the front. So then I would have the -2 times a -3. That should be a -3 because I moved it to the numerator, over 2, and then it will be x to the 4th. I think I can start to see something developing, but let's keep going because I'm not for positive yet. What about the fifth derivative with respect to x? Then I'll have the -2, -2, -3, -4, over 2x to the 5th. It looks to me like I've got a pattern developing. So if I take it one more, I think maybe you'll be able to see it as well, if you haven't already, which would be the -2, -2, -3, -4, -5, all over 2x to the 6th. Okay. So when I have this, what I'm looking for is some kind of pattern, usually having to do with a factorial. And in this case, that's exactly what I'm seeing. So I can see now that what I want to do is I do want to cancel that very first -2 over 2 and allow that to be 1. So over way back up here, I can go ahead and cancel these guys out. And then I could rewrite this one just as 1 over x. And then I could write this one as negative 1 over x squared, right? But from that point on, I've got a factorial that's developing. So again, I've reduced this and it's left behind a negative 1. And then you can see that the factorial is going to start developing from that point on. So these are canceling. Let me see what else is canceling. Scroll up a little bit. So these are canceling, and that's canceling with that. And they're all leaving behind those negative 1s. So now if you look at the numerator of each of these, hopefully you can see that I'm starting to get a factorial developing. I have a 2. Well, first I had a 1. That's in the second derivative. I have a 1. And then I have a 2. And then I have a 2 times 3. Then 2 times 3 times 4. 2 times 3 times 4 times 5. The next one will be 2, 3, 4, 5, 6. That's a factorial. So now the trick is to try to come up with a formula that represents that. So usually you start one step at a time. So we'll start with the summation. And remember that the formula that we're looking for is the nth derivative with the center plugged in, that's a, over n factorial times x minus the center to the nth power. That's what we're looking for. Okay, that's our formula. Now, if I'm looking for that formula, what I want to do is kind of look at this and figure out a pattern for this part of it, because I already have the pattern for the n factorial and x minus a to the n. The only part I don't have a formula for is this part, but I think I can find it. So what I'm going to rewrite it as is the sum. And I know that the denominator is n factorial, and I know it's x minus 1 to the n. So I think that's what that part of the formula is. The question is, what's the numerator part? So if I'm looking at just the numerator, it looks to me like when I do the sixth derivative, I have x to the sixth in the denominator. Fifth derivative, x to the fifth. Fourth derivative, x to the fourth. Back it all the way back to the very beginning. Second derivative, x squared. First derivative, x. The zeroth derivative is the only one that might not work. And in fact, in this case, it doesn't quite work because it doesn't give me the natural log of that value. It takes it back to natural log of 2. So what we might have to do on this one is chop off the beginning, the first term, and come up with a formula for the ones after that, because the natural log of 2 doesn't fit the rest of the pattern. Remember that when we plug in the constants, we're supposed to be getting a pattern here, and the first one doesn't fit. That means I'm not going to be able to take it back to starting at n equals 0. I'm going to need to start when n equals 1. So down here, I'm probably going to need to start with n equals 1. And from that point, then the numerator part of the constant is based on this formula, which is going to be over x to the n, so matching whichever derivative I'm doing. And then I need to figure out what the pattern is here. This is 5 factorial, which is 1 less than the power in the denominator. So I would write that as n minus 1 factorial. Now I have a number of negatives attached. I have the negative 1 from the very, very first cancellation, and then each one of these carries a negative on it. And they'll always carry a negative because the powers in the denominator are increasing, which means that when I bring them to the numerator, they're still always going to be negative. So this is going to give me 1, 2, 3, 4, 5 negatives, which is the same number as the factorial. So then I can multiply this by negative 1 to the n minus 1 factorial. And it looks to me like that will generate all the terms in the series except the very first one. So in order to write it out, I would start and write the following, that this series is going to be given by the natural log of 2, take the constant you can't make fit the pattern, and then write the rest of it. N equal 1 to infinity. And let's see, could I simplify this? I could simplify it a little bit, right? I could take my n factorial that's in the denominator up here that came from this part of the formula, was not a part of the derivative part. And I could write this instead as n times n minus 1 factorial. And then I could cancel my n minus 1 factorials. And that will give me a slightly simpler formula now. So now this will let me write -1 to the n minus 1 power. I can drop the x to the n to the denominator. So this can drop down here next to the n in green that got left. So I have n x to the n times x minus 1 to the n. And that would be a formula for the Taylor series, right? So this is the Taylor series. For the natural log of 2x, natural log of 2x centered at 1. Okay? All right, so that, hopefully that helps. If you set -1 to the n minus 1, does it still alternate? Yes. The only thing that will, because n minus 1 is still going to change even, odd, even, odd. The only thing that will stop it from alternating is if you force it to be even. And that means 2n or 2n plus 2. So the only way to guarantee you always have an even is to make it be even by multiplying by 2. And then you could add or subtract an even number. An even plus an even and an even minus an even are always even. So long as it alternates between even and odd, it will alternate sign. -1 or positive, negative, and so on. Okay? All right. So do you guys have another one that you want to see, or do you want me just to pick one? I am happy to pick. I'm looking to see if there's another. That one's a little bit tricky getting it into series form because there's this leading term that is never going to fit the pattern, so you have to pull it off. Let's see what else did I do. I haven't done 10 or 11 or 12. Let's try 12. And then 14. Okay. And 6, 3, 17 as well. Oh, let's do 17 now since it's a natural log as well. Okay. In the power series. Okay. All right, so I'm looking at this one. All right. So 17 is another natural log problem. Okay, so let's look at number 17. It says the function is natural log of the quantity 3 minus x, and it's represented in its power series form as the summation of some series of constants multiplied by x to the nth. In other words, it's just your normal power series. So we want to find the form of it. In order to find the form of it, we first need to put it into a typical format. So in order to put it into the typical format, one of the easiest things to do would be to rewrite it so that we have 1 minus something related to 1 minus something related to x inside inside the argument to natural log. Okay, having a hard time talking today. Okay, so let's start with this one up here. So what do they mean? They mean you need to take this natural log of 3 minus x and rewrite it so that you can end up with a natural log of 1 minus something with x. All right. So that's the typical form that we have for a Taylor series. If you look in the textbook, this is the one for which we have a known formula. So there's a table in the book, and I also gave you a table of the known power series, and this is one of the ones that we know. So we have a formula for natural log of 1 minus something, and it ends up being, let's see if I can find it real fast from the textbook or from the internet. Let's see. Known power series formulas. Known power series. Okay, here we go. Known power series formulas. Images. Okay. Let's start. I'm looking for natural log. Let me put in natural log and see if that one will pop up. I have natural log of x, natural log of 1 minus x. I suppose we could develop it. There it is. Okay, let me see if I can get a copy of it. That is not a good picture. Let's see if that's a better picture. Hang on while I find a better picture. That's a terrible picture. It's not very clear. I think that's the one I'm looking at. Okay. All right. There we go. Okay, so let me copy and paste it down here. All right. It's not a great version of it, but this is probably one of the better ones I can see at the moment. Okay, so here's the formula for the natural log of 1 plus x. Now, where do you get the natural log of 1 plus x? How do you make that into a Taylor series, or how did they even find that? Let's talk about that, because that may be part of the problem, is you don't even know where these are coming from. So for example, if you were given this natural log of 1 plus x, how did they come up with this on the right? Remember that you could let this be some function. You could call this f, which is the natural log of 1 plus x. But remember, we're allowed to do the derivative or the integral term by term of any formula. So for example, on this one, if I wanted to do the derivative of that, what would it give me? Well, the derivative of f, which would be, of course, f prime, would give me 1 over u, 1 over 1 plus x, and then times the derivative of u, which is still 1. But I could write this, which is the derivative of that, into a power series formula by writing it as 1 over 1 minus a negative x. And then I could take the negative x and put it in parentheses, And this part I can definitely write into my power series formula, right? Because this has a geometric series form. So this is negative x to the nth power, with the negative x being inside the parentheses. So this is how they came up with it. And then, of course, if this is what the derivative is, how did they get back to the natural log of 1 plus x? Well, they need to undo the derivative. So what they did to get back to f was they integrated it term by term, and they chose the first constant, of course, to be 0. So that's what they did. They wrote this out. They wrote out some of the terms of this, which it would alternate. So this would give us, let's see, the first one would be a 1, right? And then the next term would be a negative x, and then the next one would be a plus x squared minus x cubed plus x to the fourth, dot, 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 and so on. And then they integrated it, right? They took the integral of the whole thing. So they integrated each step right here on the whole thing all the way across. And all of this, of course, with respect to x. So I should have differentials on all those of dx. All right. So when we look at this, this is how the formula came into being. This is where the formula came from. So, but for now, we can simply start with this formula and apply it to what we have. So in order to apply the formula here that we've got, we need to look at this and get it into that format. And the format that we've got here is 1 plus something involving x. And we've got a 1 minus. Okay, so I could rewrite this one then as, instead, let me get rid of some of these windows that are open. Close that down. Okay, so what I need to do then is rewrite this as 1 plus. So now I've got a negative something with x in order to use that formula. So in order to do that, I've got to rewrite this 3 minus x. So the first thing I'm going to do is factor the 3 off of the 3 minus x. It's not a common factor, but you are allowed to do that. So I'm going to represent the argument to natural log with square brackets, and I'm going to factor the 3 off of those two terms. And that will give me 3 times the quantity 1 minus x divided by 3, right? And then the next thing that I need to do is to pull this apart, because I need just the 1 minus something with x in it, not this extra 3. But I have a log property that says if I have the product of two things both inside the argument to log, I can rewrite that as the sum of the two logs. So this gives me this right here. So it's just sort of using an algebra trick to rewrite it. So now that I have it in this format, I can take the formula that is here and apply it to this part of it, and then add the natural log of 3 onto the front of it. Okay, so let's go ahead and write that part out. So this will give me natural log of 3 plus. Now I need to rewrite this with a plus instead of the minus. So I have a natural log of 1 plus, and then I'm going to write this as negative x over 3. Now this looks exactly like the formula, so I can expand it if I want to, or I can write it in the power series form. I'll do both. So in the power series form, it should be negative 1 to the n minus 1, negative 1 to the n minus 1, which will alternate because n minus 1 will change even, odd, whichever signs you've got, times x to the n over n, right? So that's the formula in power series form. And then you've got to figure out where is this starting. And in this case, it's going to start when n is 1. because the first term, just like in the last problem we did, the first term is a natural log and it doesn't fit the rest of them. So we're starting at 1. And this will generate this list of numbers, natural log of 3 at the front, plus if n is 1, 1 minus 1 would be 0, so the first one's positive, so that would give me x over 1, which is just x. And then the next one, when n is 2, I would get 2 minus 1 is a 1, so that's an odd number, so it will be negative x squared over 2, and then continuing like that. So you can see that the pattern is the same, except for us, instead of substituting x, what are we going to substitute in place of x? Kind of need more space. Instead of x, we're going to be substituting x over 3 with a negative on it, because that's what ours is. If you look up here in our formula, that's what's replacing the x that you see here. Oops. Okay. So then our next one would be minus, in parentheses, negative x over 3 squared over 2 plus, in parentheses, negative x over 3 cubed over 3, and then so on, minus dot, dot, dot. Okay, so that's our pattern. So they've asked us to find C sub 0, C1, C2, C3, C4. Okay, so when we're looking at C sub 0, that's the very first term, which is the one that you get that doesn't fit the pattern. That's the natural log of 3. So this one would be natural log of 3. And then what about the C1? C1 would be the coefficient on the next term, which if I were to simplify this would just be a negative 1/3. And there's not a lot of space in those blanks, so I'm having to use those sideways fractions I hate. Now, if I were to look at this term right here, and I were to simplify that, when I square the negative x over 3, the negative goes away and I get 1/9, and then I have to multiply it by a negative 1/2, which will give me a negative 1 over 18, or if you want to leave the fractions there, I get a negative 1 over 2 times 3 squared. It does come out to be negative 1/18, but again, if you multiply those out, you're going to lose the pattern. So then the next term, I would have a negative raised to an odd number, so it's going to be negative 3 to the third times 1 over 3. So the next one is going to be a negative 1 over 3 times 3 to the third, which would be 3 to the fourth, which would give me negative 1 over 81. And then the next term, we would have a 4 in the denominator. This negative would be raised to the 4th power, so it'd be positive, and I'd have 3 to the 4th. So this last one, I'm kind of running out of space. Let me change color so it contrasts. I would have 1 over 4 times 3 to the 4th. I believe that's what I would end up with. And did we say it was positive or negative? Oh, it would be negative because of that negative right there. In fact, it looks to me like they're all going to end up negative because the pattern itself alternates sign, but because we substituted a negative inside in place of x, those also alternate. And when this is negative, we have even powers, so this is positive. And when this is positive, we have odd powers, so this is negative. So I think after the natural log of 3, they're all going to be negative. All right. Okay. Now, what about the radius of convergence? So coming back to the original, what we substituted in place of x was negative x over 3. So just like we looked at it and we were able to write it in this formula, it will converge whenever you have that less than 1. the absolute value of negative x over 3 less than 1. Now the negative will go away because you're taking the absolute value. And the next thing you want to do is you want to put it between negative 1 and 1 and write this out. And I noticed on the quiz that I was grading from last week that you guys are doing exactly what I told you not to do. You're skipping steps. I know it's arithmetic, but you're skipping steps and you're messing it up. So write it out and actually do it. Stop skipping steps. I have students who are, adding 2 to negative 1 and coming up with 0, and it doesn't work like that. So multiply by 3 on each of these and, slow. Okay. And that should end up giving me that it's got to go between negative 3 and 3. So the radius of convergence on that one would be 3. Now to find the interval of convergence, you would have to take the 3 and plug it in to see what you would get if you put 3 in for x. And if you put 3 in for x, in whichever formula you wanted to look at it, I don't know if it would converge or not. I think not for sure at 3, since natural log is not even defined there. And at negative 3, it might. So I would leave it like that. Okay? X to the k over k. Okay. Questions about that one? That one's kind of a hard one. I mean, it is the last one, but it is a fairly difficult problem. Okay. See, what were the other ones I said I was going to look at? 12, let's look at 12. 12 is a little bit different. Okay. All right. And then I want to look at one out of the next section. Separate the page. Okay, so here's 12. 12 is the power series for e to the x centered at negative 1. This one should be a pretty straightforward, pretty simple one. Natural log can get a little tricky because you end up with 1 over u, and then when you take the derivative, they're all rational functions, so they get more complicated as you go along. But let's take a look at this one and see if we can develop the Taylor series for it. So first thing we want to do is to find all of our nth derivatives. And then when we're done with that, we'll take the center, which they gave us as negative 1, and we'll plug those in. Okay, so the first thing I want to do is compute my derivatives, but that's easy because the derivative of e to the x is always e to the x. It's never going to change. So e to the x is one of the simplest ones to do. If you have something where you have like e to the 2x, you get a powers of that number attached to it. And I think there's one in here like that. If we have time, we'll take a look at it. So now what would happen, no matter what I do, I always have e to the x. So what do I get when I plug in the center? Well, e to the negative 1 is 1 over e. Right, which is a constant. It's a relatively small number, but it is a constant. So now find the Taylor series for it. All right, well, the Taylor series formula is the sum from n equals 0 to infinity of the nth derivative with the center plugged in, which in our case is always 1 over e, over n factorial times x minus the center, which is a, to the nth power. Okay, so now that we have that and we can plug in the rest of it, we know what our formula is going to look like. This is going to give me, let me give a contrasting color. In this case, the sum from n equals 0 to infinity. All of my derivatives are e to the x. Plugging in the center -1, I always get 1 over e. So I get 1 over e over n factorial times x minus a -1 would make it +1. And that would be raised to the nth power. Okay. Oops, got a little carried away on my x there. All right, and that's it. That's the formula for the Taylor series. It's essentially done. No matter what, that's what it's going to come out to be. Okay, what about that one that I said had powers of e? Where was that? It was in here somewhere. Maybe it was after that, so that you can compare the two. Where was that? Nope, it's not that one. Nope, 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 no, no, no. Ah, there it is. Okay, it's number 4. So let's take a look. I don't think I've done 4 yet. So let's take a look at 4 and compare it to the one we just did so that you can see how it's different. Or not different, but what gets added to it as a consequence of not having just x in the power. Okay. All right. So this one is a little bit different in that the center is not -1, the center is 1, and instead of just having x in the power, we have 2x. So watch what happens with the 2 that's in the power. It's going to do something kind of different. So again, first we start with the nth derivative of the function, and then we're going to plug in the center, which in our case is a 1. Okay. So the zeroth derivative, of course, is just e to the 2x. So that doesn't do anything. And then when I do the first derivative, I get an extra 2 at the beginning for e to the 2x. And then the second derivative is going to give me another 2. And if I did the third derivative, I would get another 2. So in fact, what I'm getting is a developing series of 2's at the beginning, and the number of 2's I have matches the derivative number that I took. Since this is the second derivative, I have 2 2's. First derivative, I have 1 2's. Zeroth derivative, I don't have any 2's. Third derivative, I'd have 3 2's. And then when I plug in the center into each of these, e to the 2 times 1 is just e squared. And this would give me 2e squared. And this would give me 2 times 2e squared. And the third one would be 2 times 2 times 2e squared. So the second Taylor polynomial, P2 of x, would consist of, remember the formula, so the first term is going to be e2 over 0 factorial times x minus the center to the 0th. The next term is going to be the first derivative, so the n value is 1. So I get 2e2 over 1 factorial x minus the center to the first. And the next term is going to be the 2 times 2e squared over 2 factorial running out of room, x minus 1 squared. So you could simplify that if you want, but from there we could also write down the formula for the Taylor series, which I think is the part some of you are struggling with, is how do you find that formula? So from this one, if you look at the pattern, the denominator is 0 factorial, 1 factorial, then it'd be 2, then 3, then 4. So the denominator is going to be n factorial. And we definitely have x minus 1 to the nth power, since this matches that. But this is the only part of the formula we don't know. And from what we found up here, it's going to be e squared times increasing powers of 2. So it's going to always have an e squared in it. The first one does not have a power of 2, but the second one does, and the third one does. So notice that the number of 2's you have is 1 less than this power, which is the value of n. Did I say that right? No, I guess it matches. Yeah, if this is 2 factorial, I have 2 2's, 1 factorial, I have 1 2, 0 factorial, I have no 2's. So I would make that 2 to the nth power. That will work because 2 to the 0th is 1. And then I can start at 0 and go to infinity. Okay. Is there a sheet you can print off with the known power series? Yeah, there is a list out there on D2L that you can use. There's one in the book, but I think I also made a list for you. If you go into Professor D's material, you'll find it in there under power series. There should be a handout of known power series. The ones that you need on the test, I will give you on the test. I'll write them on the test so that you have it in the form I want you to represent it in. Let's take a look at one more off of this homework set. There was one that's more similar to what you'll be doing in the next section, 6.4. So I wanted to look at it. It has a cosine in it. Where is that? Where is it? Okay, now I can't find it. Where did it go? No, it's not that one. 14. 14. I want to look at the last part of number 14. All right. Okay, so here's problem 14. When you're looking at 14, they want you to come up with a Taylor polynomial of degree 4 for cosine of x with the center being 0. That's really a Maclaurin polynomial. And then they want you to approximate 1 minus cosine of x over x with that polynomial, and then evaluate the limit. Now, this is one of those limits that you learned in Cal 1. And the value of that limit is 0. I'll tell you that right now. It is 0. It is an indeterminate form because if you were to plug it in down here, you do get 0 over 0. So it is indeterminate. We can solve this using L'Hopital's rule. If I apply L'Hopital's rule, I get 1 minus, what do I get? 1 minus a negative sine of x on top. Oh, wait, the 1 goes away because I've got the derivative. Okay, so the 1 is gone. And then limit, and in this case, x is going to 0. And then the derivative of x is just 1. And a double negative makes it plus, and the sign of 0 is 0. So I know the answer there is 0. All right, so that is known. But the question is, how could you do this with series? So what we're going to do instead of, what we're going to do is we're going to find the Taylor series, and then we're going to use the Taylor series to evaluate this limit. All right, so we're starting with cosine of x. And we're going to do the nth derivative at x, and then we're going to do the nth derivative at 0, which is our center. And this is actually a Maclaurin polynomial. So if we start with the original function, which is cosine, and this is the zeroth derivative, of course. And then the first derivative would be negative sine. And we'll probably go, I don't know, at least until we see the pattern. And then the second derivative is negative cosine. Third derivative is sine. And the fourth derivative is where the pattern begins again at cosine of x. All right, so we've now got the repeating pattern. From then on, it's going to repeat every 4. So if I plug in the center, then the cosine of 0 is 1, and negative sine of 0 is 0, and negative cosine of 0 is negative 1, and sine of 0 is 0, and then it repeats. So our repeating pattern is 1, 0, negative 1, 0. So I'm going to write that here, 1, 0, negative 1, 0, and then it repeats, 1, 0, negative 1, 0, and it goes forever, right? That's the numerator of the coefficient factor. So again, our formula, n equals 0 to infinity, nth derivative at the center, that's the part that is fulfilled by this. This part here is this pattern, divided by n factorial times x minus the center to the nth power. Our center is 0, so x minus a just becomes x. So our pattern then, I'm going to write out the terms. The first coefficient in the numerator, I'm going to have a 1. So I have 1 over 0 factorial x to the 0. And then I have plus 0, because the next term is going to go away because of the 0 there. Then minus 1 over, this would have been my 1 factorial, so now I have 2 factorial x squared. And then the next one, of course, goes away again. And then I have, so 1, 0, negative 1, 0, 1 again. So then I have a plus 1 over, that's 3 factorial, so this is 4 factorial x to the 4th, and then 0 again. And then I have a minus 1 over 6 factorial x to the 6th, plus 0, plus dot, dot, dot. So let's write out the formula then for cosine. So cosine of x is represented by this power series, which, well, let's, instead of doing the power series, let's go ahead and write out the terms. So 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th minus 1 over 6 factorial x to the 6th, and then it goes on from there. Waiting for it to finally finish drawing. Yay! Okay. So then it keeps going from that point on, dot, dot, dot. And then once I have those terms written out, then I can more easily see the pattern. So again, the first term doesn't always give us the pattern, but the second, third, fourth, and so on will. So it looks to me like I have a sum. I'm going to have an even number for the factorial and an even number for the power. So the only way to get an even is to multiply by 2. So in parentheses, I need a 2n factorial, and I need an x to the 2n power. Now I want to have this one be 2, so that would be if n is 1, and then when n is 2, I'd get this, n is 3. Going backwards, would it work then if I started at 0? If I start at 0, 0 factorial is 1, so that's okay. And x to the 0th power is 1, so that's okay. So that will take care of that. And now I need to take care of the alternating signs. So to do the alternating signs, I can take a negative 1 and I need to raise it to a power so that the first one is positive and then it starts with the negative after that. So I can just raise it to the n and that will work. Okay, so this is my formula for cosine. Now, the third part of this problem is the one I want to look at, the one I want to focus on, which is use that to find this limit, 1 minus cosine of x over x. So this is exactly the kind of thing you'll be doing in section 6.4, in addition to binomial series. So when I'm looking at this, I want to use that to find the following limit. Okay. Eeks, trying to get it. There, perfect. Okay. So find the limit as x goes to 0 of 1 minus the cosine of x over x. Yeah, that's what it is. Okay, so what I'm going to do instead is I'm going to write this into here instead and then evaluate the limit. So if I look at that, I can write the limit as x goes to 0 of 1 minus, and now I'm going to substitute this infinite polynomial here into those brackets. So 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th. I'm running out of room. Minus 1 over 6 factorial x to the 6th plus dot, dot, dot. And divide all of that by x. Okay. So if I were to plug this in here and then I need to distribute the negative, what's that going to do to my signs? Well, it's going to make this a negative and that a positive, and that will be a negative, and that will be a positive, and that will be a negative. But this will give me a 1 minus 1, or 1 minus 1, yeah. And if I have 1 minus 1, that goes to 0, which means that in my next iteration, what I now have left is the 1's canceled, and I ended up with, when I have the signs changed, 1 over 2 factorial x squared minus 1 over 4 factorial x to the 4th plus 1 over 6 factorial x to the 6th minus dot, 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 all over x. Because I was able to get rid of the constant 1 minus 1, when I look at this now, every single term in the numerator has at least one x factor, and the denominator has an x factor. So I can, since I have a monomial denominator, I can divide each term in the numerator by x and rewrite it. So this gives me the limit as x goes to 0 of 1 over 2 factorial x, because x squared divided by x is x, and then minus 1 over 4 factorial x cubed plus 1 over 6 factorial x to the 5th minus dot, 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 right? Because all I did was take the x squared, divide by x, x to the 4th, divide by x, x to the 6th, divide by x again, and then plug it in again. Only now every single term has at least one x factor, and x is going to 0, which means I get 0. And that's another proof that it comes out to be that way. So this is problem 14. Yeah, 14. But it is very similar to part of what you'll be doing in 6.4. There are two main parts to 6.4. Limits like this, and then the binomial series. So you've already seen this limit. This is one thing we use power series for, is to evaluate limits that might be difficult in other circumstances. This one works okay with L'Hopital's rule, but that's not always the case. Okay. I'm going to work on your review today, so hopefully I'll get that out there later today so you can look for it. I'll post an announcement when I get it done. Are there any other questions that you guys have? See you guys tomorrow, so have a good day. At least it's nice and sunny today. We can go outside, although It's still kind of snowy, but it didn't really stick. So, all right, see you guys tomorrow.